Hello, everybody. Today I will be talking about our paper Asking the Right Questions, Facilitating Semantic Constraint Specification for Robot Skill Learning and Repair, with myself, Aaquib Tabrez, and my colleagues from University of Colorado Boulder, Jack Kawell and Bradley Hayes. Within the last few decades, there has been a significant interest for the development of collaborative robots or cobots that work alongside humans in close proximity safely and efficiently. But most of the current systems deployed in factory settings are brittle to changes in the environment, which is common when it comes to collaborating with people in close proximity. Additionally, these collaborative robots are going to be deployed for everyone, not just factories, such as in assistive robotics, elderly care, or even household tasks. While working closely with people, these systems need to adapt to preferences of different users. For example, if robots get too closer while cleaning the house, some users might find it uncomfortable. These preferences cannot be coded beforehand as they are specific to individual users, so ability to account for user preferences is also something lacking from current systems. Finally, as these robots are going to be used by everyone, but they are prohibitively difficult to train and needs experts training them. We have moved from manual programming approaches to learning from demonstration approaches, but even these approaches, such as kinesthetic teaching, teleoperation methods, are also not user-friendly to non-expert users. To summarize the motivation of this work, current collaborative robots lack the ability to handle changes in environment, are not readily accessible to handle user preferences, and are not easily programmable for non-expert users. In this work, we introduce parsec, plan augmentation and repair through semantic constraints, an algorithm for enabling people to use natural language for more easily selecting, annotating, refining, and parameterizing constraints on robot motion plans. Parsec empowers non-technical users with access to constrained motion planning techniques, provides a route to safer, correct by construction robot skills regardless of the underlying model. To give a broad overview of how parsec looks like, first, our system detects skill failure as shown in the video clip on the left, where robot's arm is very close to a person while clearing the table. When system notices skill failure, it queries user to determine the reason for failure. Users are interactively guided through the constraint annotation process through semantic interaction. Once the reason is determined, robot can apply skill correction to successfully execute the task as shown in the right video clip, where robot maintains a safe minimum distance from the human. To give an example of how constraint annotation looks like, or how the interaction between human and robot looks like, first, robot asks a very broad question on failure to get initial feedback on skill correction. For example, it can ask that, did I do something wrong? Based on the feedback user gives, it can determine the root cause of the failure by iteratively questioning the user. Here you can see human replies, you were too close to me, and then robot finds that human wants it to maintain safe distance of 50 centimeter all the time. Finally, after determining the constraint which user wants to apply, parsec can successfully apply the constraint to its motion planner. Before we dive deeper into parsec's formulation, some of the preliminaries we need to know is that parsec is a post hoc method, that is, it is applicable when learning agent has been trained to execute a specific task in the training environment. To illustrate, if a robot is tasked with cleaning, it should know cleaning task beforehand. Users can add user preferences such as how close it can work with them or where things can go and such. Furthermore, parsec is independent of underlying learning model as it is applied post hoc. For our implementation, we use concept constraint learning from demonstration, or CCLFD, from Muller's and other, an extension of kinesthetic keyframe based LFD that allows addition of high-level constraint information to demonstration data. These constraints are the high-level concepts encoded as Boolean signal, such as keep the cup upright or keep minimum distance, which are not modeled by robot state data alone. To get into the details of Parsec's algorithm and flow, first, robot executes skill alongside human teammate and observes human for skill completion. If it detects no skill failure, it does nothing. If it detects a skill failure, as shown in this clip where robot is working too close to the user, our system creates a parsec tree. Parsec tree is a tree of available constraint functions and their potential parameter assignment. The core insight is that by structuring constraint using constraint function, we can significantly accelerate constraint discovery. This is an example of the parsec tree where fully parameterized constraints are the leaves of the tree. Intuition here is to guide the users to select a particular constraint and values of its parameter. Here, blue nodes represent the parameter types, red nodes represent both grounded parameters such as cup and lifted parameters such as angles, or combination of both. Green nodes represent fully parameterized constraints available for the planner. This tree is created by organizing the nodes such that each parent node is subset of its children, where additional detail is added as we move down the tree until fully parameterized constraint is reached at the leaves. We can view it as a simple 20 question styles depth first search to find the constraint, but as you can see, it can easily become tedious. To improve the search of constraints further, we utilize feedback from the users, which is divided into 3 steps: requesting for the feedback, processing the feedback, and using that to rank the tree nodes. In the feedback step, user is requested to provide general information on how skill can be corrected, and this open-ended explanation is passed by our NLP engine to score each node of the tree. For example, if the robot's domain knowledge consists of the words computer and person, and user provides the explanation that don't move near the computer, the scoring process will give high value to the computer and a low value to the person. Once the ranking of the nodes is done, they are sorted by the score, and we use it iteratively to ask user to hone in on the desired constraint by traversing the tree. And as soon as we confirm the desired constraint from the user, agent can apply the constraint to the motion planner. We repeat this process all over again, correcting one constraint at a time to improve the skill. With this, we can guide users to semantically modify or adapt robot's plan to successfully execute them. To evaluate the novel capability of Parsec, we developed 3 case studies. Each involved correcting general purpose skill using different approaches and comparing them. For the case studies, each skill were trained with CCLFD for both success and failure. Failure case was achieved by removing an important constraint which system needs to find from the user's feedback. We recorded videos for both these cases and allowed participants to watch them through the survey. They were allowed to watch it as many times as they can, and participants were asked to describe how each skill can be corrected using single sentence explanation. We initially had 19 responses, but we had to discard one participant's response as they did not follow the instructions that were given to them. Going into tasks, we had handover task where robot attempts to give a cup to a user but spills the contents in the process. This is an example of faulty training where training model does not have the constraint of keeping the cup upright. Second task is the pouring task where robot is tasked with pouring contents into receptacle on the table. Although the skill has been properly trained, but receptacle has moved from its position during the training. So robot pours the content in the wrong position over the table. This demonstrates a situation where skill has been correctly trained, but not robust to the changes in the environment. A constraint that requires the cup to be above the receptacle during the pouring motion will correct the skill. And the final task is the cleaning task, where the robot moves a cup across the surface of a table in front of a user who is performing another task. As you can see, robot moves too close to the user, causing discomfort. This scenario represents an example of training that does not represent user's preference for how a robot should act when it is working in close proximity. We use three different approaches to evaluate. First, NLP method or semantic baseline, which iteratively queries each leaf of parsec tree based on ranking scores. It is simply going through all possible constraints that are available based on ranking score. Second is tree method or naive exploration method, which uses parsec tree for exploration without using ranking mechanism. Finally, we use full parsec algorithm with tree scores. For the evaluation, what we do is that we use the explanations we got from the survey and apply one of the three methods for asking questions. We calculate the number of questions asked before the correct constraint was discovered, and that is used as our evaluation metric. We had two hypotheses going into this. First, we hypothesized that number of queries in parsec condition will be lower compared to the other conditions. And second, we also hypothesized that naive exploration parsec tree and full parsec algorithm will outperform the semantic baseline. The intuition behind the second hypothesis was that using parsec tree data structure would reduce the time to find the constraints. We ran ANOVA between the three conditions and found a statistical significance in all the three conditions, proving hypothesis 1 that parsec algorithm needs least number of questions to discover the constraint compared to the other approaches. Similarly, we can see hypothesis 2 was proved with statistical significance, that is, using parsec tree data structure reduces constraint discovery significantly. To summarize, what parsec enables today is that it empowers novice users without prior experience in robotics to access constraint motion planning, and it also allows user to incorporate unique preferences and changes in the environment that happens during the runtime. With this, I would like to conclude my talk. Thank you for watching this presentation.